Thank you. Hello, everyone, and warm welcome to the 23rd lecture in the series of Cloud Physics lectures conducted by IITM Pune. And today we have a distinguished scientist, Yangang Liu, Dr. Yangang Liu from Brookhaven National Laboratory and Environmental and Climate Sciences Department, New York. And we want to welcome you to this lecture series, and he will be talking on using knowledge on cloud microphysics and cloud radiation interactions to improve solar irradiance forecast. So little bit more applied field also. So let me also welcome Dr. Sudarshan Dara, one of our scientists, to introduce Dr. Liu and also give a brief introduction about his talk. Thank you.
Okay.
Sudarshan.
Okay. Good.
Hello.
Hello.
Yes, please go ahead.
Yeah. Good evening and welcome to the 23rd lecture of Cloud Physics lecture series. So today's speaker is Dr. Yangang Liu, who is a senior scientist at Brookhaven National Laboratory, Environmental and Climate Sciences Department, New York, USA. I will just give a brief introduction about the speaker. Dr. Liu has completed his BS and MS degree in atmospheric science from Nanjing University of Information Science and Technology, China. Then he has completed his PhD in atmospheric science from Desert Research Institute, University of Nevada, Reno. His research interest mainly on aerosol, cloud, and precipitation and their interaction with climate and weather. He has more than 200 plus research publications. He is also an adjunct full professor at Stony Brook University, New York, USA. A brief of today's talk is as follows. Solar energy has become an increasing important source for renewable energy, calling for accurate forecast of solar irradiance. The highly variable nature of clouds and their interaction with radiation poses daunting challenges to solar forecast that is based on either observation or numerical weather predictions model. His talk covers two parts. First part focuses on observation-based model, which are often limited to largely to forecasting global horizontal irradiance, GHI, or direct normal irradiance, DNI, over relatively short time horizons, that is less than 1 hour, and lack clear physics and clarity of interpretability. He will also present a theoretical framework that links GHI and DNI with cloud properties, a hierarchy of 4 physics-informed persistence model based on theoretical framework that can be used to simultaneously forecast GHI and DNI and diffuse horizontal irradiance, DHI. The second part is introducing research on their group on improving the physics-based weather research and forecasting model, which is specifically used for solar forecasting scheme, and that is WRF solar. In particular, he will discuss parameterizations of turbulence, entailment mixing processes, DNI, and their implications into solar, WRF solar, and influences on solar forecasting. With this, I invite Dr. Liu to present his talk.
Thank you very much, Sarah and Sudarshan, for the nice introduction and also invitation. I'm honored to give her the first talk this year. And today I'm going to introduce briefly my work on kind of new venture for me on solar forecasting. Can you see the screen?
Yes.
Yeah, so the title of my talk is using knowledge on cloud microphysics and cloud radiation interactions to improve solar radiation forecast. Before I start, I would like to acknowledge many colleagues over the years, as you will see, and a lot of work, although the project is relatively new, but a lot of work has done long time ago. And especially I would like to mention my postdoc and the students who did this, have done this work. I'm talking about today, modeling and machine learning. And the work is supported by US different agencies, ARM, ASR, the Solar Energy Office, also ASCRA, that's a supercomputing. So this is the outline of my talk. I will start with some background motivation and then introduce the data-driven forecast model, and then talk about a physics-based numerical weather prediction model. For this case, is WRF Solar, and then a summary. So, as you know, just some background. This is a cloud physics lecture. So I'll just start with some background knowledge about cloud physics. So really, cloud physics is started really pre-1940s. It's kind of people based on some scientific curiosity. People started to do empirical studies of cloud physics, and really rigorous study of cloud microphysics. Cloud physics really started in the 1940s. That's is a weather modification. I heard from Sarah there are still a lot of activities of cloud seeding going on in India. And in the 60s, 1960s, the climate model and the numerical weather forecasting model started to, and there are also large area simulation models and other limited regional models. They all started around 1960s. And so my early work kind of around the weather modification, the climate and the weather forecast model and the cloud resolving areas models, modeling, and try to improve these the models. And recently, I kind of venture into this new field. That's a new application of cloud physics, I think. Solar energy and wind energy. Today, I'm going to talk about the solar energy in particular. So why we need to do solar forecasting? So to combat global climate change, there is a great surge of using renewable energy, try to make the energy sources sustainable. But renewable, including solar energy, and as good as the solar energy is, there are some challenges to do it. Here is a list of few. One is we know the solar energy vary a lot. Therefore, it is challenging to maintain it in the grid, in the electricity grid, like reliability and the stability of the grid. And also, there are some difficulties to integrating the solar energy system into existing power structures. And also, if you do forecasting, the economic value. One example is stock trading, because it's people trading energy actually need to know the forecasting at a very short time horizon to make trading. So therefore, and actually solar energy forecasting is more challenging than climate and weather forecasting in the sense that they require forecasting at ranging from a very short time horizon to a very long time for planning. So I kind of clouds are major challenges, as we know, right? Because for solar forecasting, this is come to the utility of the cloud physics. So one of the reasons I mentioned, clouds vary substantially, also very quickly, right? And also, clouds have a variety of different shapes and structures, and clouds interact with ambient aerosols and other meteorological variables, including wind, that makes the synergy between wind, the solar, another different challenge. I'm not going to talk about today. And then clouds also have strong interaction with the solar radiation, as we know already. And also, clouds not only are key for improving climate and WP models, as I mentioned, and is more challenging to forecast solar energy in a sense than forecasting climate and weather, because the need for global horizontal solar irradiance, the GHI, and the direct norm irradiance, that's DNI here. So there is a basic, you need to not only forecast to know the total radiation, you need to know the partition of the radiation into direct and diffuse radiation. Another thing is we need to know to do the forecast in very short time horizon. That's about a minute up to the a very long time scale at climate scale for planning purpose. So here's the summary about a general approach people have been using to do solar forecasting. So one is a data-driven approach, like kind of in the bottom part. That's mainly for a relatively short time horizon. And then is NWP-based forecasting. That's for relatively longer forecasting lead time, right? And so, of course, the challenge for how to do both, not both, all the to do forecasting over all the time horizons. So the idea is what we are using is try to prove the data-driven models in this direction, and then try to improve the physical-based and WP model forecasting in this direction. So let's say the first part of my talk is data-driven models. We know now the AI and the machine learning models are almost buzzword in not just the our field, the other field as well. But there are a lot of, although there are a lot of advantages of the data-driven models, there are some limitations. Here's a list of few here. The bullet here is one of the things, the main thing is the lack of clear physics. So the machine learning model almost like a black box, right? Is kind of like our traditional statistical model is actually more so because of a deep learning evolved. Another thing, because of lack clear physics, and then the model lacks interpretability. It's very hard to interpret the results of the model, and therefore attribute any issues, errors, forecasting errors, or improvement to any physical reasons. And like I mentioned already, is normally as data-driven model are limited to short forecasting time horizons. So one of the reasons people have been working on, including myself, is try to incorporate physics into data-driven models. That's I'm going to show you today. So speaking of physics, we know clouds affect radiation a lot, tremendously. It's a major problem. How to represent clouds in climate and the weather forecast model is a major challenge. The same, very similar issue for solar forecasting, right? Because the strong impacts of clouds on solar radiation transfer, of course, including long wave, but not directly related to this talk. So this is a cartoon of the solar of clouds. When the solar radiation penetrates the clouds, then the solar radiation will change, right? And so this is the first order approximation. It's a work, but kind of based the work we published about 10 years ago. Is kind of refreshing. We find a new application in a very different field. Okay, this is the first order approximation. When solar radiation penetrates the clouds, then the radiation will change. Well, because the cloud droplets will scatter the radiation, therefore, you will cause diffuse radiation. It's here. And then there is another part that doesn't change direction, we call it a direct radiation. Okay, there is an issue then. We have a total radiation, we are partitioned into DNI, the direct and the diffuse radiation. So in climate and the weather forecasting, at least now, we are only concerned, we primarily concern the total radiation. But for the solar energy field, we need to know both total and the direct radiation, because different sensors use different, collect different part of different components of the radiation. Okay, so anyway, through this process, about 10 years ago, in this work listed here, we developed a theoretical framework that kind of relate the partition of the total radiation into direct radiation, diffuse radiation, into two key cloud properties. That's cloud fraction and the cloud albedo. Okay, it's kind of the equation is listed here. I'm not going to go through the details. People are interested, you can take a look at, contact me, or just read the papers. So here is a cartoon, just give you a visual idea why this is the case. So the top one, the top figure shows this is, I think this is the cloud albedo. Oh yes. Well, there are some type of this. The first one is cloud fraction. Sorry, this should be a cloud albedo. Anyway, so this basically show for this per cloud fraction case, you can see it only depends on this B2 parameter. That's really determined by the DNI. And the bottom one is mainly determined by this ratio B1 divided by B2. That's mainly determined by the ratio of the ratio of the total versus DNI, the direct radiation. Okay, this is a visual show you. So demonstrate. This is the model result. Demonstrate our theoretical framework actually works. So this is a kind of another list of the equation we use in the solar forecasting model. Oh, I call it the simple physics. Right. The key thing I want to emphasize is by using this, allow us to separate the effects of cloud fraction and from the cloud albedo effects on solar radiation transfer. But of course, you need, in addition, the need for total radiation, you need the direct radiation component. So then, based on the theoretical framework, we can basically build a hierarchy of models with different physical approximations. It kind of listed in this table. Okay, the first one, there's no assumption evolves, so there's no physics, right? So it's like just direct use the original measurements. Then you reduce the cloud effect into overall cloud effect. That's what I mean. Like the clear paper, the so-called smart persistent model that is widely used in solar forecasting. That is based on clear sky index. Basically, that considers the cloud effects, but does not separate the cloud albedo and the cloud fraction effects. The third level approximate model is based on the B parameter I just mentioned. That's kind of related to cloud fraction and cloud albedo, but not exactly, through some approximation. then the most accurate way is consider cloud fraction cloud albedo directly. It allows to separate. So then we play with this different. The first work we did is to play with the simple physical model with different approximations or assumptions into the persistent model, and then we got the results. So the results is shown in the bottom plots for total radiation, GHI, and total radiation, direct radiation, diffuse radiation. And this is the forecast accuracy versus leading time. So the general thing you can see is as we go up from the level, from first to fourth level, so the model of the forecasting accuracy generally improves. That's one thing I want to mention. And also, by the way, the data we use about more than decades, the data collected at ARM SGP site. And the accuracy improve also increase with the leading time. That's a very good sign, because that's one of the reasons we want to increase not only increase the forecasting accuracy at a particular leading time, but we also want to extend the forecasting horizon of the model. That's show this is possible just by demonstrate by using a very simple persistent model. Demonstrates this idea. If you incorporate the physics at a different degree, you can increase the forecasting accuracy. At the same time, extend your forecasting leading time. And so the next work we did is extend the simple physics-based persistent model into more complicated machine learning model, kind of following the current trend. What we tested here is, along with some more, we also tested some more advanced statistical methods like ARIMA. So we tested the machine learning model is a long-term, short-term forecast model than the SG Boost. Okay? And what we did is kind of like before, we built a hierarchy of model, and in order to test the physics, try to get the physical explanation why we get improvement and how. So we build a hierarchy of models, is starting from univariable. But by there, in the forecast, we only use GHI or DNI or DHI. And then we use two variables, and that's like you use GHI and DNI. And then we add another component that's all sky information, also corresponding clear sky information, irradiance. That's kind of like our physical framework. We need to have this. Right? That's what we can start bringing our theoretical framework with different approximations here. And then lastly is the complete the machine learning model based on our most complete theoretical framework. That is the basic cloud albedo cloud fraction. Again, the results show here is forecasting accuracy versus leading time for different models. So without going into the detail, the message I want to say is, so the machine learning model, if you use a more complicated machine learning model, does improve the leading time and the forecasting accuracy compared to for the same, if you use the same physics incorporation. And then also the higher the model we go, as before in the hierarchy, the better the accuracy, the better the model forecasting. That means the better the forecasting accuracy, or the longer the forecasting leading times. Another thing, the results based on both the simple physics-informed persistent model and this more complicated machine learning model demonstrates that basically two things I want to emphasize. One is just by incorporating very simple physics between cloud and radiation interaction, we know from other studies, and into the data-driven model, the model can prove we can improve model the forecasting accuracy and the leading time, extend the leading time quite significantly. And also, of course, now we are clear. The key, another thing is we are clear about why we get the improvement and how we get the improvement. Another thing I want to emphasize, probably useful, have this emphasize that it would be much better to forecast GHI and the DNI, or the total and the direct radiation simultaneously together, because they contain much better cloud and radiation interaction physics. If we only do GHI or DNI, we cannot catch the full scale of the physics yet. And this information probably would be useful for climate and NWP model as well, which I'm probably thinking to do in the future. Yeah, any questions so far, or you want to continue?
Yes, please continue.
Okay, so this is the first part, data-driven model, and so the next part of my talk will be focused on how to improve NWP model. In this case, is WRF solar. That's the weather forecasting WRF model, weather forecast research model tailored for solar forecasting. So this is a general view graph, and just illustrate what we do at the lab in my group. And so we know climate, the weather, and including solar are very complex and multi-scale phenomena. Therefore, at least right now, we don't have the way, because of the computational limitations and the knowledge limitation, we don't have a one unified model to cover all the scales we want to stress, all the scales and the phenomena we want to study. Therefore, we use different type of models to do it. Here I listed here direct numerical simulation model, large eddy simulation models, the cloud resolving model, NWP model, and the climate model. Different corresponding different phenomena, different scales. What I want to mention, I've highlighted through this plot is probably except the particle result direct numerical simulation model, all these models need to parameterize or approximate cloud microphysics in the models. In our jargon is parameterization. And then people use different parameterizations to different approach to develop a parameterization, cloud microphysical parameterizations. This is a kind of a cartoon to show why do we need parameterizations, in particular for WRF solar model. Just like a climate model, we can generally represent the model in this way. There's resolved physics or dynamics, and the unresolved subgrid processes, which I call the fast physics. And then there are a lot of fast physical processes going on in the atmosphere, and in the WRF solar model in particular. So here I list a few examples which I'm interested in been working on, as cloud microphysics and turbulent neutrino mixing, the radiation, and in particular, like I mentioned earlier, and for solar forecasting, we not only need the total, but we also need the partition of the total radiation to direct and diffuse components. And turbulence convection, the PBL, the boundary, planetary boundary layer structure, and the aerosol, of course, aerosols. So for today, I really focus on the microphysics and the effects of turbulent and trim mixing on microphysics. I know there are a lot of very similar research going on in IITF. So here is this is the first work we did, just to give you an idea of why we care about cloud microphysics in solar forecasting. What we show here is the forecast of leading time. This so we test the Wolf solar model with different microphysics schemes, right? And for different color corresponding different cases of the clouds we selected. We basically select about 8 cases, and including stratiform clouds and the convective clouds. They are all boundary cloud, by the way, because we focus on warm clouds in this project. And then where the vertical axis shows the difference between the maximum and the minimum value, right, for different schemes. You can see there is a very high sensitivity to different cloud microphysics scheme, depends on cloud type, also depends on the time, the forecasting leading time. The general message I want to convey is the solar irradiance reaching the surface, just like precipitation kind of, very sensitive. How do you represent the cloud microphysics? That's the key message I want to convey through these slides. And then we work to try to replace existing microphysics schemes. Some of the existing microphysics involve solar, implement the microphysics schemes developed at the lab. So some of you know we have been working on try to develop cloud microphysics schemes. ICARs give acronyms like aerosol cloud entrainment. There are a few key things I emphasize in developing this parameterization. The first thing I kind of emphasize is we would like to try to derive the parameterization from physical principles as much as possible, even use approximations. And by doing that, that allows 2 things. One is allow us to reduce the number of tunable parameters that is built through the empirical parameterizations. Another is like that allow us have a very clear physical meanings of tunable parameters. Even you still have tunable parameters. You have a much clearer physical meaning of these parameters. Another thing I want to emphasize in my research is we need to consider the effects of spectral shape of hydrometer spectral distribution. That is, for this particular case, really is a cloud droplet size distribution. We need to consider the spectral shape, because most of the parameter that requires really 3 moment schemes eventually. And another thing that has been lacking is a parameterization for turbulent and trim mixing processes. So recently, I kind of, with others, have a review of this topic. And if you are interested, you can take a look at this paper to see some detail about what I mean about the ACE parameterization we've been trying to develop. It's still in developing stage. So today, the talk are really going to show the spectral shape, and then the 2 topics, then the turbulent and trim mixing process. Of course, they are all related to each other. What do I mean by spectral shape, in particular relative dispersion? So relative dispersion is a parameter, a non-dimensional parameter I use to represent the spectral shape effects in models, in parameterizations, and that's the ratio of standard deviation to the mean radius of a droplet population. So the cartoon show here is basically example of you use different relative dispersion. These three plots show here is they all have the same total number concentration, the liquid water content. The only difference is the relative dispersion. So you can see the spectral shape himself is very different. You would imagine they should have some strong effects on all kinds of cloud properties just by visually looking at this plot. Here's two examples about the importance of relative dispersion. The left-hand side, what I show here is the cloud radius property, specifically is cloud albedo and the cloud radius forcing on the right-hand vertical axis. What I show here is the cloud albedo under the assumption it's monodispersed. Cloud droplet population that's normally people do, and then the difference between the real one, you use a real relative dispersion, relative to the monodispersed one. Okay, there are two things. One, you can see the effect. There are strong effects, and depend on the value of relative dispersion. And another one, there is a very interesting, that's surprising to me when I saw these results. And there is a peak. The effect of relative dispersion, there is a peak, and the peak value is corresponding to a cloud albedo is around 0.5-ish, right? That's the typical we would see in ambient clouds. That means the ambient clouds, for some reason, kind of emphasize the effect of relative dispersion, the spectral shape, right? Just in terms of cloud albedo effect. And the right-hand side is the effect on autoconversion. Autoconversion is the first process we used in the cloud microphysics parameterization from cloud water to rainwater, right? And then autoconversion process is in there is basically two function approximate formulation. There is the threshold. That means the threshold function, normally we use Kessler type, Sundquist type, and the Berry type empirically. If people are familiar with this field, there's not clear physical meaning, but through this theoretical work, which is listed here, is we basically demonstrate by varying relative dispersion, you cover all the empirical types from Kessler to Berry type. That means you use different type. Actually, that means it is implicitly contain the information of or represent the information of relative dispersion. So by the way, the effects of relative spectral shape on cloud properties without aerosol getting involved, I call dispersion bias. There is another topic, which is when we consider aerosols. That's the one I'm going to introduce now. This is a well-known phenomena since Toomey in 1974. That's what I quote here. What he found is when you have in a cloud polluted environment, you have a lot of aerosol particles, more aerosol particles. Therefore, your droplet number concentration increased. And then other things being the same, you get a smaller droplets, more clouds, more reflective. That's we call the increase. Because now some people call first indirect aerosol effects, but I would like to call. I think we should call a number effect. Droplet number concentration, of course. By reducing the droplet sizes, you also reduce the efficiency of rain formation, and then make clouds last longer and maybe thicker. That's called second indirect aerosol effects. Okay. And of course, this picture is very much simplified, and there are a lot of things have not considered. So one is I'm going to show next is I call it dispersion effects. This kind of modified view is so when you increase or changing the aerosol concentration in environment, you not only increase the number of droplet number concentration, at the same time, you actually make the spectra change the spectral shape of droplet size distribution. Through the change of the shape of droplet size distribution, there is a additional effects on cloud albedo, which I kind of call the dispersion effects. So when we first did the work in 2002, and we found the dispersion when aerosol including aerosol loading increased, the droplet number concentration increased, but the relative dispersion increased. Therefore, the effect is reduced the cooling caused by increased the droplet number constant, the number effect. But since that publication, a lot of other studies, including ourselves and some wonderful scientists in IITM, they found some of the results support our finding in 2002, and then some of the results are not. And then since then, and people, including ourselves, developed a very extended regional understanding is a dispersion effect actually can either reduce the cooling in aerosol limited regime when aerosol is relatively low, but enhance the cooling of aerosol indirect effects in updraft limited regimes whereby the aerosol loading is relatively high. When I say relative, really relative to cloud dynamics, updraft velocity. Dispersion effects is much more complicated than it used to be, but they are important. And that's another reason why do we want to include a relative spectral shape effect in microphysics parameterization. Another thing is I mentioned about the theory. Here is I want to introduce the theoretical work we did in terms of ring initiation. Because this theory is relatively unknown. They were published in the physical review letter instead of in the physical review instead of in the typical earth science journal. So the left-hand side show, I call it the value of death, borrowed from my colleague Barry Wiscombe. Where the idea is, so what I show here is the growth rate radius versus radius. We know for typical regular condensational growth, the growth rate decreases with the increase in droplet radius. And the collection process, collision coalescence process increase with droplet increase in droplet radius. But in order for collision coalescence to start, you need some large droplets around probably 20 micron radius-ish. Okay, that's why I kind of valley-like. So this is a lot outstanding puzzles in cloud physics people have been working on for a long time, still working on. There are a lot of theories proposed to explain, including turbulent and trim mixing. And so with my colleague and Bob McGuire, we propose a kind of a theory we call it connective potential theory. And when we published the paper, now I tend to call system theory because it's connected with the system theory we've been developing for cloud droplet size distribution nicely. And also really for this, the theory, the key of the theory is to looking at the particle population as a group instead of individually. Okay, anyway, in the one sense, is like the theory is like this. So this is you can think of energy. So the formation of rings like a barrier crossing process. So it's kind of like nucleation, right? Aerosol activation. Once you you go over the barrier, then the reinformation starts spontaneously. Okay, and now based on this theory, we can define the critical radius widely used in representing auto threshold function in autoconversion processes. And most of the schemes, empirical scheme, they treat it as empirical value. Now we have a theoretical basis for this critical radius, and based on this, we actually derive a theoretical relationship with this critical radius, this corresponding this peak. Like function look like this. It's a function of liquid water content, L, and a drop number concentration N here. So now we have a theoretical expression and for critical radius, and then by combining this expression critical radius we have, and with the other theory, other part of theory for collision coalescence process, we can derive theoretical or autoconversion parameterizations, a number of them, and with different approximations, theoretical approximations anyway. And in the jargon, AGU figure out when they write a highlight for this to figure out a title, will build a better virtual raindrop. That's basically what we try to do, and we try to understand the formation of rain, also to parameterize this process in the cloud microphysics parameterization from first principles as much as possible. So another thing I have been working on for some time is turbulent and turbulent mixing processes. This cartoon shows what I mean by that. And the general thing is when you have clouds really are open systems, interact with the environment. And you can bring the dry air in and then mix with the clouds, and then clouds population will react. Depend on the structure of the clouds, and then the cloud microphysics will react this, the mixing process will react the intrinsic air, dry air very different. There is a cartoon show here. We call it homogeneous mixing and the extreme inhomogeneous, anything in between. And this is my colleague Chun Song figured out this economic analogy for people who are not in this field to understand this. So almost like if you have this example, if you have a company with 10 employees and each employee's salary is $10, this is the company to pay the salary about $100. And then during economic crisis, so the company only have about $90. How are you going to distribute the money among the employees? There are a number of different ways. This is two extremes. You can decrease the salary to all employees without fire anybody. That's called homogeneous. And then you can fire somebody and decrease some salary of some employees, but not all. That's the extremely homogeneous. So there are all ways in between that can happen, very similar to clouds, right? This is the same thing for clouds. So this is a complication of turbulent and turbulent mixing. It's a phenomenon that people know for a long time, but we still struggle to quantify it and understand it physically. This is another cartoon shows the same thing. Basically, the Dom-Cowan number is a non-dimensional number defined as a ratio of turbulent mixing time versus turbulent microphysical time. In our case, we call evaporation time, drop evaporation time. It is a function. This one is a function of depend on this ratio, and you can have all kinds of different behaviors. Therefore, you would think we need to represent this process in the model, but we don't. So far, we have not. People just start to work on to do this. This is basically a study show you even probably the best type of model used to study clouds, that's a large area simulation model. And show here, we compare the RES model with measurements, and then where we show on the right-hand side the drop radius, volume radius versus liquid water content. The bottom one is the model result. You can see is almost like homogeneous mixing behavior, but in observations we see is almost like inhomogeneous mixing behavior. Okay? This basically demonstrates what we expect, kind of, without representing this untrimmed mixing process in models. We cannot catch the full scope of the cloud microphysics. Okay, we get, in this case, we get some part of the wrong. You could get the liquid water content right or number concentration right, but you probably cannot get your radius right. The radius we know is important for radiative properties and also the precipitation formation. So now we've spent a lot of time trying to figure out almost a decade's work, figure out how we're gonna simplify our understanding in a way that so that we can represent in the model. So we know this mixing diagrams. What it shows is the kind of the size of the droplet population is the number. Depending on the mixing behavior, we can have all kinds of things. The horizontal lines represent the inhomogeneous mixing. Doesn't change the size, but it changes the number when the mixing happens. And this one is a homogeneous mixing, and the number concentration decrease, the size decrease as well. And they can have a very different behavior like this. But how we're gonna represent this phenomenon with one parameter? Here's what we figure out with the angle. Here, with this angle beta here. Depending on the value of this angle, and then we can quantify all these different mixing from the microphysical point of view. That's basically what we figure out. And for us, we can play with different measures, but generally speaking, the idea is very similar. Use one metric or one measure to quantify to represent all the different mixing processes. This is the first thing we did, and then the next thing, of course, is to how represent the microphysical measure in terms of dynamical measure, which we can predict. That measure, the microphysical measure, as good as they are, still cannot be represented in current two-moment scheme, for example. We still need to do some simplifications. And to do that, we did basically two things. One, we know the dump cone number is a good one, but to get the dump cone number, we need not only turbulent dissipation rate, we also need the entrained dry air eddy size, which is, at least now, is hard to know. So we need to further simplify it. And Lehman in 2009 has a nice work. It's called the transition scale length. Define this basically define as the entrained dry air size at dump count number equal 1. And then relate to this transition scale length too, the entrainment different mixing process. And so get rid of the need for entrained dry air size. That's a simplification. We borrow that idea and define that as by divide the transition scale length through the common of micro microscopic scales, this eta here, and make it non-dimensional, called transition scale number. So we use this transition scale number to parameterize the microphysical measure I just showed you, the angle thing. That's what we've been trying to explore. First, we explore this with the measurements. This is a show on the top panel here. Well, by the way, what we show here is another matrix, microphysical matrix defined here. So then later on, we found out some differences between, although general idea follow our expectation, but different clouds have different behaviors. And then we play with, we test this with some EMPN model developed and Trimmin, and the possible modeling developed by Steve Kruger at Utah University, and they ran a lot of cases. And we generally we found a very similar behavior, but also found the relationship between the parameter A and B through that study, the modeling study. That's what it shows here. And this is the one we implemented in our model testing. The results are reported here. We also tested other forms parameterization. They show some similar results, but one thing I want to emphasize, to mention here is right now this mainly developed for two-moment microphysical schemes, and the effective spectral shape is still a wild card. There are a lot, the entrainment mixing process himself depends on the spectral shape as well. So it's still waiting for rigorous solutions. We implemented the schemes in our Wolf solar model and tested different cases. And this is the example here. What I show here is a time, and this is the difference between the scheme that use this scheme and the scheme without the scheme. Right? This is this is so time. Sorry. Yeah, the different color is a different ways we represent the turbulent dissipation rate. But anyway, the general idea is that the entrainment mixing process has a strong effect on where we get the solar radiation at the surface. Right? And then if we're looking at a different way, the spatial distribution is that is a domain average, like I showed previously. This is a time snapshot of two different times, the spatial distribution of the total radiation and direct radiation, diffuse radiation, the cloud fraction, the cloud albedo. Okay, you can see the effects of much more stronger. Because you can have, using different ways to represent your entrainment mixing process, your cloud structure changed, and therefore your radiation, spatial distribution of radiation changed as well. If you do a domain average, you can tend to reduce this variability a lot. That's the message. Yeah, this is, I just talk about, in the project, we also develop radiation parameterization, his partition. I don't have time to talk about today, but if you're interested, you can contact me, I can send you the papers. And another thing, we know the system for climate or atmospheric process that involve clouds are much more very complicated, including Wolf solar. There are a lot of processes need to parameterize. There is a list of some of the key processes here, and they all interact with each other. Therefore, we need to eventually we need to improve, just like climate model and the weather forecast. We need to improve all these processes if we really want to get to improve the forecasting accuracy. Another thing is we have been trying to do that I don't have time to show is there's you have parameters still, even without parameterization, there's still some tunable parameters in the parameterizations. And how we're going to tune these parameters online right now, offline tuning. And basically, using AI and the machine learning type, we can tune automatic tuning that combined with data simulation. And that's another way, another type of work we need to do if we want to improve the forecasting model. And yeah, this is a special issue on fast physics and JGR a couple of years ago, and talking about their paper talking about this different topic in more details if you are interested. This is take-home messages. The first one is really proper consideration of just the simple physical relationships between clouds and the radiation interact and the radiation can improve the data-driven models a lot. And we need to consider the total and the direct radiation together because it contains much more complete cloud radiation physics. And in terms of improving physics-based model, we need to consider spectral shape and also turbulent mixing processes. So our work just a start. There's still a lot of room to improve, which is my future work, and also there we need to have a better integration of data-driven model and the physics-based models. With that, I'll stop here and take a question. Thank you for your attention.
Thank you, Yangang, for a very wonderful lecture. And Sudarshan, I don't see any questions in the YouTube. Maybe if there, maybe then we can take questions from the panel here. Bipin, you wanted to say something? Yeah.
Hi, Yangang, it's really very good talk. And you have covered a lot of things. Some of the work I already know. And the new things which you are actually putting into the future also and future work, and also you explained something about the machine learning model where you have used LSTM XGBoost. Those models are really good, but the thing which you are planning to do with the physics-based model, what does it mean? You are going to apply the machine learning into the equations, or you want to use the physical variable in the as an input in the machine model? What is your plan?
Right. By the way, very nice to see your face again, baby. After some while.
Yeah.
And thank you for the question. So right now, for this particular project, what we have done is to base our theoretical physical understanding of the theoretical framework is we reduce original variables, solar irradiances, into non-dimensional numbers. And then we perform the machine learning models. So it's like we incorporate the physics by first reducing the data from based on physical understanding. And then we apply the machine learning model. That's right now for this particular work we have done, but we cannot always do this, right? Have the very nice physical understanding or theoretical framework allow us to do, and we're also exploring, kind of like you mentioned, incorporate the equations directly into machine learning model, and to add physics that way. And actually, we explore this idea in we have projects of for the particle result DNS. One objective of that project is try to add physics by physically constrain the model when we develop machine learning model. That's so in a way So we use both right now. We explore both basically.
Okay.
To answer your question, Bruce. Yeah.
And your existing models, what LSTM and XGBoost perform better than other. So did you try even more dependent variables? Whatever is dependent, you did the forecast of solar radiation, no? So maybe some other variables you can put as an input, which are having very good correlation with the your predictor, a target variable, and then you can try and it can give better results. I mean, this is my experience with other data, which happens.
Yes, that's a very nice question. Actually, we have done that. The Weijia, the student, now she graduated, and so we consider we are writing the paper now. We consider aerosols, wind, and the temperature.
Yes.
And because our theoretical work right now only consider clouds. And so in order to get cloud properties, you also need other variables to predict cloud properties. Yeah, that's what, like you said, we explored that. We see some improvement, and for example, if we consider aerosols, we see some improvement. And yes, to answer your question, yes, we explore some other variables. We also explore the performance of the model for different cloud types.
Yes.
For example, yes, and because I have a different cloud types, they perform differently. Because the theoretical framework we have to develop, we know it's based on plane layer assumption, assume a single layer of clouds over there. That's not realistic. Although you can get a cloud fraction albedo approximately, but there's the first order approximation. We have not really considered cloud structures. Once we ran into, say, for example, convective clouds, the 3D structure of clouds is important, which I have not considered. And we expect that there is a larger error for that type of cloud. So our analysis shows that's the case. Actually, the model performs worse for deep convective clouds. So that means we need irradiation representation. We need to really consider cloud structure, including the 3D structure.
Okay. Yeah. In summary, I will say that we can put the more variables, but we have to be careful. We have to first do the pre-processing of the data. What variables should be included in the training or not? So that pre-processing can be done in advance before putting into the model.
Yeah, thanks for the suggestion. Yes. I'm no expert on machine learning, so in the team we have somebody working on this. So yes, we found very similar issues actually for the machine learning model. It's not sounds. I mean, the talk makes the machine learning model sound very simple. Actually, it's not.
So, I mean, generally people are blaming that machine learning as a black box and they are not performing well. But I mean, it is not completely true. We can get good results if we are very careful to prepare the data.
Yeah, and yes,
But you have found some improvement with the machine learning model included with the physics, right?
Well, actually, that one is amazing because that does not increase computational time. Yes. Because the first step reduction of the data from the regional data to non-dimensional data based on our theoretical understanding is relatively simple, and the machine learning model doesn't change.
So my question is that the machine learning model, for example, for the entrainment process, maybe did you consider it in a very high resolution, or how did resolution also can play a very big role when considering the entrainment process, right? So how did you?
Yeah, actually, right now, that's a great question. Using machine learning to consider intrinsic mixing process yet. So right now, in terms of intrinsic mixing process study, kind of like you guys, so we basically explore this with three approach. One just from measurements, with measurements, whatever measurement we get, collect a different sampling frequency, different scales. And another one is use the EMPM. That's basically the model Steve Kruger developed as a one-dimensional partial model considering intrinsic mixing. We also try to, in developing partial model ourselves, try to consider intrinsic aerosols. Another is the DNS, like BP has been doing. And one of the limitations BP know much better than myself is DNS is very time consuming. So we did some work, and the BP and the others also done some work, but the domain size is a major challenge for us. So that's why another reason we try to use see whether we can increase domain size by bringing the machine learning idea into PRDN and the DNS model. So we basically use the three approaches right now, but we haven't really explored the machine learning modeling to intrinsic mixing process per se. So.
Okay, I have one question regarding see some of the studies show very clearly that for example the Elias versus observations, Elias show more homogeneous mixing. So what is your explanation for that? What do you? Yeah.
Yeah, our current understanding is because in the areas, at least the one we tested, so that you assume all the say the particles or the microphysics exposed to the same thermodynamics and dynamical property within the grid. Therefore, basically that follows homogeneous mixing assumption. So all the droplets exposed to the same environment. Right, that's kind of fit to our understanding. So therefore, if you want to consider, the representation of intrinsic mixing process in ERES, you really need to bring other things. So our parameterization is relatively simple because we are targeting. We try to reduce the computational time, not increasing computational time a lot by adding this process, by considering this intrinsic mixing process. There are other studies, like I'm sure you know Hoffman and others, they are using much more complicated way to represent in the model. But I would think that way is needed, but probably not. Will not be used in like areas of climate and the weather forecasting or renewable energy forecast model for in the near future.
Okay, I think Sudarshan,
there is a question in YouTube. So I'll just read out it. A question from Palas Sinha. The question is, what are the major components that we need to look in microphysics for simulating weather extremes using NWP for better skill in terms of intensity, duration, and timing?
Oh, that's a tough question. Thanks for the question. This is my personal take. Right? If you want to consider extreme, of course, all the things I'm talking about is important. Right, the improving, they are related to improving microphysical parameterizations. But I would, in terms of the extreme weather, I would mention the ice processes, which I have not discussed. I have not done much study in my research. The ice process is probably more important than the things I'm talking about here. Of course, that remains to be seen. The outer conversion process is definitely very important because it involves rain formation. And but ice processes, that's really a wild card, in my opinion. One of the reasons I have not really done much on ice processes because I figure we have not really understand simple warm clouds yet. So yes, that's turbulence definitely is another thing we need to do if we want to study extreme weather, because that involves wind. We have another project try to improve wind is so the turbulent dissipation rate representation of that one in the model is need to be improved a lot. Right now there are a lot of issues with it. That's another thing in my view. I might be wrong this way. I haven't really done any concrete study on the effects on extreme weather. That's my guess from my understanding of the problems.
Okay. Are there any more questions, Sudarshan?
There is no more questions in YouTube.
Okay. Any of you have any further questions to Yang to discuss?
Yeah, actually, I have one question. Actually, in one of your slide, you have shown the diurnal variation of solar irradiance differences for different microphysics scheme.
You mean the solar radiation?
Yes. For different microphysics scheme, you have shown their time variation, and there is actually the peak value is coming at different times for different microphysics.
Yeah, that was in the first part.
What's the question?
My question is, how microphysics controlling that peak time for the solar irradiance? Is it due to cloud fraction, or like microphysics, like drop size distribution is playing a role in that case?
Yeah, I think you refer to this one, right?
Yes. Lower panel, yeah, right.
Yes, and I think the answer is probably is all above. We haven't for this particular view graph we show here. We test the existing microphysical schemes. I think we test in the world solar.
Okay.
So we test, I think is probably 7 or 8. I forgot exactly. It's not our own scheme, so we cannot tell exactly whether it's a spectral shape effects or is it because of the intrinsic mixing. But I can tell you from once we implement our own scheme, we did explore the effects of the spectral dispersion, also the turbulence and intrinsic mixing effects. And they both can affect this solar radiation reaching surface. Depends on the types of clouds. Can have very different effects. And I didn't have time to show. I probably can show you here. There is hopefully I can find this one. Can you see this one? I didn't talk about the radiation parameterization. One of the things we developed with collaboration anywhere, scientists at anywhere, Yu in particular, my former postdoc, is to get to the radiation, both the total and the direct radiation, is a very challenging task. Because all the compensating errors between different components. And so what we demonstrate here, eventually, if you want to improve, like for example, when we consider turbulent and intrinsic mixing and the dispersion effects in our microphysical schemes, we can get the total radiation improved, but the direct radiation is sometimes getting worse. If we want to get both right, we have to consider the total the radiation parameterization. In other words, for this particular one, we try to improve the direct radiation, the DNI part in the radiation transfer. We have to do both if we want to get all these components right. This is the result shown here. Is basically it's a 1 year forecast at RMSGP by comparing the default model and the one with our upgraded microphysics and the radiation. So to answer your question, yes, and both the dispersion and trim mixing process, they all play a role in the radiation forecast in this, but they can be their role can be different for different type of clouds or different times. And another thing is to get all things right, we at least we need to consider radiation as well. In other words, the representation, not the total radiation, but actually the partitions total radiation into direct and diffuse radiation. Right, that's kind of a challenge that are very specific to solar radiation forecasting, at least now.
And also probably the interaction between the microphysics and the radiation scheme also makes a big difference, right?
Yes, and how like a lot of microphysical model parameters that have not connect to the radiation transfer yet. So the scheme we tested the scheme we tested in existing in World Solar, a few schemes that actually connect their microphysical scheme to the radiation scheme. Therefore you have a better representation of effective radiance, among other things. Yes.
Yeah, thank you. And Sudarshan, are there any more questions in the?
No, there is no questions.
Anybody else want to ask any question? Yeah, Sudarshan.
Yeah, I think I have. I have one more question actually. Already, Dr. Liu has mentioned regarding the ice process. Actually, in our region during monsoon, most of the clouds are having top in cold region. So we have mixed phase ice and liquid. Both hydrometeors are present. So in that scenario, like how good is those parameterizations applicable for solar radiation forecast?
Oh, you mean your observations?
No, not from observation, from model point of view. I mean, whatever model development, whatever result you have shown, my point is those are mainly for the liquid phase of the cloud you are considering, right? Like this entrainment effect when you have the liquid phase and dispersion effect. But my point is when there is both liquid and ice, both particles are present, then how it will behave and how, I mean, applicable are those parameterizations?
Oh, I think in my view is like I said, warm cloud are always part of the either mixed phase clouds or ice part clouds. They almost always, right? So therefore, no matter what, they are important for mixed phase clouds or ice clouds because they can affect how much water you bring up in your supercool clouds, and that will affect, say, the latent heat release and then the dynamics, other things. But beyond the effects through the liquid processes, the ice process themselves are very important. Which I think there's one example is the hydrometer, say the ice crystal or snowflakes, the geometrical shape. and the rhyming degree. Those are the things are represented in the model now, but I think it's very, much more with a lot of approximations, much more approximations we use in warm phase processes, including, for example, the entrainment mixing process, right? I would think maybe, which this is the maybe actually more important than in ice processes than in warm phase clouds, because the time scales are very different, and the dynamical structure sometimes can be weak, like cirrus clouds, and the rhyming degree and the hydrometer shapes. In my early days of research, actually, the hydrometer shape is a part of my research interest. I've been trying to use a fractal idea to represent the hydrometer shapes, the self-affine fractals, to characterize that. But I think there's still how to make make the connection of the fractal parameters like fractal dimension and the perfect and the power laws to the specific physical processes. That's still something need to be done.
Yeah. Thank you very much. And if there are no further questions, then I think we can close this session.
Yes.
And we want to profusely thank Yangang to make this possible. And a long time we have been discussing on this, having this particular lecture. And we are very grateful that you are the first speaker of this year. And thank you so much.
Yes, thank you for the invitation again. Also, very nice to see the familiar faces. And anyway, you have my email. Also, anybody feel free to contact me if you have questions on my work.
Yes.
Yeah.
Definitely, all are encouraged to contact him. And if you have questions, please clarify. And thank you so much. And let us then conclude the session here.
Okay.
Thank you.
Thank you.
Thank you, Padmakar and Sarath, for you can close the session now.